Welcome to the drowsy scientist's world, where curiosity floats as science is served just warm enough to wrap you into night, while snow falls gently. We're going back hundreds of millions of years to a time when our globe was encased in ice. Yes, we are discussing Snowball Earth, a period when glaciers reached the underfrozen ice, equator life persisted, and the Earth itself may have resembled a vanilla ice cream scoop from space. And I sincerely hope that this video doesn't provide you with too many fascinating details. But if it succeeds, at least you'll be tossing and turning while learning about climatic feedback loops and ancient geology, which is a terrific deal. If before we begin, I would be quite appreciative if you could give this movie a soft like and a cozy small subscriber, which is purely for fun and significantly helps the channel progress. Tell me where you're watching from and what time it is in the comments section. Do you hardly have your eyes open at 2 o'clock, or are you winding down by 10 p.m. in Tokyo, a.m. in Toronto? Then settle in and let's take a deep breath and begin our story, which does not begin with fire. If you haven't already, close your eyes and visualize the Earth in rage but with frost. Instead, you see the blue marble that is alive now, with whirling clouds. Imagine a more peaceful, lonely world where the continents are clumped together in an indistinguishable way. Odd forms, frequently foggy skies, a dimmer sun, and let's just say that the air wouldn't be good for your lungs. This is Earth, and there are more than 700 million years ago. During the Proterozoic Eon, a period of deep time, the dinosaurs were only a cosmic fantasy in that far-off era. And at first glance, mammals were only a small part of the genetic soup. Without forests, flowers, humming bees, or screaming animals, early Earth may appear lifeless. Predators only found in large quantities of rock, water, and microorganisms. But beneath the surface, as the Earth was subtly getting ready for one of the most drastic occurrences in its lengthy and dramatic history. Something oddly certain: areas of the land were covered even though they were closer to the equator. Unlike your front yard in February, we're in ice and not just a little dusting. It's like discovering penguins drinking as massive sheets of glacier ice slowly make their way into the tropics. There was something really strange about coconut water on a Bahamas beach. But there was heat prior to the freeze, and the protozoa had their share of warmth. During that period, volcanic activity and shifting supercontinents accounted for a large portion of Earth's landmass came together to form a single enormous supercontinent known as, though not as well known as Roinia, is equally striking on its own. Ocean currents changed when Rodinia extended and fractured over the world, weather patterns and triggering the gradual grinding motion of tectonic plates. These tectonic movements were more than just geological jigsaw pieces. When Roinia started to split apart, fidgeting altered the land's balance and sea in a way that significantly impacted the climate. More coasts meant more precipitation, which indicated increased erosion, which resulted in the removal of more carbon dioxide from the atmosphere. The worst part is that CO2 is one of the primary greenhouse gases on Earth. Therefore, its reduction would result in less heat being trapped. Let's not blame poor people for the planet's gradual and unrelenting cooling. According to scientists, the sun was younger and dimmer in Roinia alone during that time. It may not seem like much, but it glowed around 6% less brilliantly than it does now. Similar to that, except on a global level, it's the difference between a comfortable afternoon and deep frost, along with fewer trees, animals, and decreased biological. So overall, you end up with a globe that isn't particularly effective at retaining heat. It didn't take much to turn the world into a true glacial because it was already skating on thin thermal ice. Earth's climate can transition into what scientists refer to as a positive climate, rather than simply dipping into winter and then back again. Feedback loops in which one consequence sets off another, which in turn enhances the initial effect, creating a kind of climate. For instance, snow and ice are highly reflective and bounce in an echo chamber. Sunlight back into space, further cooling the Earth and generating more ice. Gives the impression that the Earth has a chill since it reflects more sunlight, then continued to squeeze itself into the freezer as more ice moved worldwide from the poles to the equator. The temperature dropped, and this is where things start to become really strange. The notion that this glaciation spanned the entire planet's oceans and wasn't merely another ice age. This is the center of the Snowball Earth, including all of its continents. Imagine a picture of our planet trapped in a deep freeze, frozen from pole to pole, planetary dormancy that lasted for millions of years. But hold on. How can we be certain that any of this occurred? Because, at the time, we weren't precisely keeping weather logs. In ancient rocks, geology emerges as the protagonist of a slow-burning mystery tale, located anywhere in the world, including Canada, Namibia, and Australia. Scientists have discovered some odd glacial deposits close to the equator, which are dropstones, which are rocks that were transported and dropped by prehistoric glaciers, and they are buried under sediments from the shallow seas that were formerly heated. It would be similar to discovering frostbite in a tropical sunburn. In addition, the discovery of bedrock scratches from glacial striations caused by shifting ice and strange chemicals, signs in marine sediments, and the argument becomes more compelling that the world was cold. extremely chilly, not only in isolated areas but, of course, everywhere. A slush ball is suggested by some scientists, but everyone agrees on the entire extent of the freeze. An Earth scenario in which the equator was partially encircled by open water, though not quite a complete deep freeze. The ice is nevertheless harsh and chilly. Consider it the distinction between an ice cube and a frozen smoothie. But even if it wasn't a flawless snowball, the data suggests that there was a period when ice extended farther and was the longest known epoch in Earth's history. A period when Earth actually struck the pause, life had to change or die. But then, and we'll leave things there tonight in the silent, ancient, and strange world before the ice. Just starting to enter the coldest phase it has ever experienced, so prepare yourself and cuddle up. Chapter 2. When the globe starts to freeze, and the frost becomes more intense. Imagine standing on a rocky seashore outside, where the waves are calm. The coolness stings your skin, even if the wind is cold, and the horizon is uncomfortably white. Massive, sluggish, sparkling glaciers in what should be the tropics. It's the kind of scene that would make even a penguin wonder. Bit much, isn't it? As it moves gradually toward the equator, is more than just a cold winter day. It marks the start of Earth's most catastrophic ice age. However, a Snowball Earth event that caused a planetary deep freeze was not something that occurred overnight. It was a slow-motion catastrophe that took place over thousands of millions of years. But when it got off to a good start, things quickly became icy. So how exactly does a cascade is the main suspect after the planet unintentionally locked itself in a freezer? Earth is a drama queen when it comes to climatic feedback cycles. The ability to swing wildly when the appropriate dominoes fall, and among the first two, as we mentioned in the last section, carbon dioxide was the tip over in our scenario. Furthermore, the fragmentation of Roinia revealed new rock and formed new coasts. These rocks were worn down by the weather, wind and rain, which started a process. When silicate rocks decompose, a process known as chemical weathering, they actually draw. The process of removing carbon dioxide from the atmosphere is gradual, but it's quite effective over extended periods of time, producing a long-term pull. Decrease in atmospheric carbon dioxide. Imagine that Earth is attempting to cool itself by breathing a little bit as well, profoundly for a bit too long. And when the CO2 level fell sufficiently low, worldwide temperatures, lower CO2 levels translate into less heat being trapped close to the surface, and more ice results from less heat. And the worst part is that ice reflects sunlight differently than snow and ice on darker surfaces, such as forests or oceans, bounce sun radiation. Albedo, which is a major, is right back into space. Player in Earth's thermostat, causing a world with lower CO2 levels to cool and produce ice. And the Earth is becoming cooler as a result of that ice reflecting more sunlight. The climatic version of someone with more ice reflecting even more sunlight in winter. Removing the blanket from your bed and then opening all the windows as a precaution, a runaway ice albedo feedback loop, as scientists refer to it, after the ice began to spread, encouraging the formation of more ice, and Earth was unable to stop it. Ice moved faster through the process from the poles, then from eventually, possibly all the way to the mid-latitudes. You're not far from the equator if you're now visualizing Earth as a slowly rotating snow globe. But the cooling ocean temperatures weren't the only thing changing. Sea ice also started to shift. Currents were slowed or changed by thickening salinity. And beneath the what little surface marine life there was in crisis due to a large number of photosynthetic microorganisms. Depended on sunlight, and light penetration decreased with heavy ice layers above significantly. Life might have been extinct in the absence of refuges, completely thankfully. Nature has many strange small gaps that allow some sunshine to have filtered in the ocean's depths, close to hydrothermal vents and through equatorial ice fissures and thinner patches. Instead of sunshine, chemosynthetic life thrived in these microbial oases by harnessing heat and minerals, vital lifeboats in a world that would otherwise be frozen and quiet. And if you may be wondering how we know that Earth is surprisingly skilled at any of this, like a detective visiting the scene of a very old crime, leaving behind clues, geologists have found strong evidence of the Great Chill. For example, dropstones are rocks that, after being transported by glaciers, fell into fine ocean sediments. After the icebergs melted, they resembled tiny geological confetti strewn across old marine beds where it should never be that this near the equator, because there are glacial scratches and striations on bedrock sculpted by the gradual wear and tear of old. These glaciers are found on rocks that are currently located in tropical latitudes. They resemble the worldwide. Timing is even more telling when sled marks are discovered in the Sahara. The similar pattern of glacial traces can be seen in rock layers all across the planet. A quick, intense warming event is indicated by the peculiar limestone layers that are abruptly followed by cap carbonates. But for now, we're concentrating on the freeze. So with ice pressing in from all sides, we'll address that in a later chapter. What caused the Earth's thermostat to become locked in the Arctic blast setting and the sides? If you were able to orbit the Earth in a spaceship, the world would indeed look like if you weren't frozen solid. You would see a bright white land ocean spherical. The atmosphere was thin and dry, with all of the clouds covered by a heavy layer of snow and ice. And strangely silent winds howled, yet the only thing to ride them were no birds. Movement was caused by deep-seated bubbling hydrothermal vents and creeping glaciers. Despite living in this icy quiet, beneath the ocean ice, persistent microorganisms clung to rocks and crevices or drifted just below the ice, consuming whatever leftovers of, although there wasn't much, the chemical energy they could find was sufficient to endure the longest, coldest night on Earth and maintain the torch of life. Since the freeze was only half of the story, but it wasn't the conclusion. Even though tail Earth turned into a snowball, it wasn't there for long. Pressure was steadily increasing someplace deep within the Earth. Even as the surface froze, volcanoes kept erupting, slowly releasing carbon dioxide into the atmosphere. CO2 started to build up over millions of years, and eventually, geologically speaking, got out of control. But we'll keep that heartwarming realization until later. Pull the blanket a bit tighter and picture a world for Chapter 3 for the time being, turned to ice and remained silent while for the sun to return. So here we are, with the planet frozen in a realm of glaciers spanning across oceans and continents buried under kilometers of ice, with temperatures so high that even in Antarctic, winter would appear balmy without any fish, trees or ferns, stillness. But the marvel is that even in a world that has been reduced to glass, life has refused to let set the scene. Earth was in this state more than 600 million years ago. The surface is completely under the control of a full-blown snowball action, covered in ice, which in some locations may be up to a kilometer thick. If we were standing there in some way, the land would be buried, the seas frozen, and the horizon would be a white infinity. The thin, colorless skies are magnified. As they go deeper beneath the cold layer of life, continues to exist quietly and tenaciously in the waters where sunlight hardly reaches or perhaps doesn't reach at all. The majority of it is microbiological. There are no animals or plants that are wailing in the present. Tiny ancient creatures that survive in the environment, such as cyanobacteria, arca, and extremos, severest circumstances possible. And if the Earth's surface were hibernating, these tiny survivors were like bright sparks concealed in the ash. Awaiting the warming of the Earth, these underwater fissures are hydrothermal vents, which might be a safe sanctuary, where warm, mineral-rich water is released into the ocean by the Earth's internal heat fluids, and these vents continued to bubble around them even throughout the snowball occurrences. Microbe colonies flourished without requiring any sunshine at all. Chemicals like hydrogen sulfide can be converted into energy through chemosynthesis. This ingenious little method is still used today in some of the most isolated locations on Earth, such as deep beneath the tube worms and clams in the Pacific Ocean create bizarre habitats around black. These vent networks may have been life's strongholds during the snowball epoch, but vents weren't the sole possibility. According to some experts, that there were refugia regions where the ice was either shattered or thinner. Possibly it was only a few meters thick toward the equator, to provide just enough light for photosynthetic organisms to survive. Imagine living microbiological mats adhering to the ice's undersides like algae growing on a frozen roof. These subterranean habitats may have mirrored the sea ice ecosystems of today. Observe in the icy regions of the Arctic and Antarctic nowadays, whole groups of the slushy ice underlayers are home to microscopic crustaceans, germs, and algae. Even on a deeply frozen Earth, dancing in slow time while suspended in briny channels didn't turn off completely, of course. If living, they were probably low-energy ecosystems moved slowly, with no significant productivity booms. Microbes multiplied less often when nutrients were limited. But life isn't selective, adapts. So let's pause to be grateful for that, since life can persevere in such harsh circumstances. Reveals something important about life and not simply the history of Earth. It is resilient in and of itself. All it needs is a niche or a break. Release a tiny beam of light or a substance to consume, which leads us to the stromatolites. The true heroes of this era are layered before the snowball. Some of the earliest known life forms on Earth were cyanobacteria, which constructed these structures. There were stromatolites all over, adorning shallow waters with their bumpy, many reef-like creatures vanished during the ice. But some might have survived. Today, particularly in warmer geothermal areas, we discover ancient silent evidence from stromatolite fossils found in strata that date back billions of years to microbial tenacity, and in a few isolated locations, such as Australia's Shark Bay, a little living remnants of the oldest life on Earth. Stromatolites continue to grow today. Now, here's a fun question to put under your pillow. Might bacteria thrive on Snowball Earth? Astrobiologists who study other freezing planets are persuaded that if life is ever discovered on icy moons, such as the moons of Europa or Enceladus, which have oceans beneath their thick ice, it may resemble the shells that survived our own snowball periods. Humming microorganisms hiding in vent systems or adhering to cold undersides silently in complete darkness. Actually researching the snowball on Earth periods have evolved into a sort of extraterrestrial life dress rehearsal. Demonstrates that life only need a small foothold in time. Not everyone made it other than warmth and brightness. It was probably a severe biodiversity bottleneck during the Snowball event. Numerous microbial lineages were eliminated, and those that remained had to develop new strategies, such as stronger membranes. Enzymes' ability to withstand pressure, cold, and salt in an odd way might have contributed to preparing the way for the subsequent, more intricate multicellular according to some theories. The stress of the snowball may have even pushed advancement of evolution when the globe abruptly thawed suddenly. Nutrients returned to the oceans, CO2 levels rose, and ecosystems restarted, and life started to diversify during that period of opportunity. Never before, but since we're getting ahead of ourselves, just imagine it for a moment. The planet is still, the surface is frozen solid, the skies are empty and colorless, and the depths are microbes silently moving forward in their icy strongholds in the dark. They were unaware that they were chanting their chemical lullabies for generations, but they were preventing the complete extinguishment of the biological fire on Earth, and the thaw would arrive in a few million years. So inhale deeply and allow in the simplest forms. Life has survived fire, ice, poison, and it's reassuring that pressure existed for so long before we ever set foot on the planet. We'll crack next time in Chapter 4, since we believe that resilience is ingrained in our DNA. Since bacteria were surviving in the shadows, we should crack open the rocks to explore what they can reveal. Silently documenting their battle in stone and ground doesn't require pen. Writes in dust, rock, and layers in the silent buildup of time compressed and solidified into memory when we wish to understand what occurred hundreds of millions of years ago, before there were animal fossils, trees, or bones. We search for the last wounds and whispers, not for diaries or cave drawings. In stone, and the planet gave us some information about Snowball Earth. Intriguing geological breadcrumbs. Let's begin with one of the most peculiar locations a geologist can witness. Come across tropical glacial deposits. These aren't your typical pebbles, are droplets of rock that glaciers carried and later deposited into. As the icebergs that have been holding them melted, soft, murky ocean sediments they quietly plummet to the ocean floor, where they eventually freeze. These drop stones, which are in place by layers of compacting silt, are where things start to become really confusing. In locations such as Namibia, Australia, Brazil, and Canada that were close to when these rocks were first placed, it was like finding a snowball fight that had started at the equator. In addition to these stones, striated pavements are also present in the summer. The grinding action of glaciers has carved grooves and scratches in bedrock. Today you can literally feel the ancient touch of a long-lost person when you run your fingertips down these grooves. Ice sheet has a very lyrical quality, akin to shaking hands with the spirit of a glacier, followed by the thin, recognizable cap carbonates, limestone and dust and strata that directly cover glacial deposits from a geological perspective. They resemble a layer of icing that has been carefully applied to the rocky remains of a frozen Earth. What makes their quick formation in shallow waters and the fact that they contain how can you move from ice-covered to molecular evidence that indicate exceptionally high atmospheric CO2 levels. In a geological moment, the question shifts from oceans to tropical carbonate seas. Is the reason cap carbonates are such an important indicator? They let us know when the end is near. Was as dramatic as the beginning when Earth eventually experienced a snowball. Thor was quick and fierce in his escape from the deep cold, and the warm carbonate-rich waters are demonstrated by carbonates, deposited the identifying minerals in a flood that swamped the recently exposed terrain formations. A flurry of chemistry and life recovery, but let's not go too far for now. Just take in the investigative job that these geologists have been assembling this tale for decades by examining isotope ratios that use radiometric dating to establish latitude and old magnetic traces to create a timeline instead than simply pointing to a rock and saying, yeah, obviously this came from 720 million years ago. It's more like putting together a 10,000-piece puzzle gradually. Unpacking some of the most captivating snowball puzzles. Earth evidence can be found in areas like Namibia, where the cap is exquisitely preserved. Glacial tillites and carbonates lay on glacial detritus that has been cemented into stone. Layers in Canada's Mackenzie Mountains demonstrate the transition from glacial deposits to abrupt tropical seas to the south. Australia, where carbonate layers and banded iron formations provide a look into when together. These worldwide hints about ancient ocean chemistry point to every continent was impacted by the planetary scale freeze known as synchronous glaciation at about the same time. But rocks don't merely document events, they also give clues. How? And that's where the narrative becomes even more interesting. For instance, some sediments include banded iron formations, which often arise when oxygen and iron-rich fluids mix. These layers suggest that the oceans, which were previously stratified and deficient in oxygen, were abruptly disturbed and may have become oxygenated. Sulfur isotopes are produced by the thaw and the rush of nascent life. Excursions in carbon isotopes that point to significant disturbances in the carbon cycle, similar to what would be predicted if CO2 levels suddenly increased following millions of years of volcanic accumulation beneath the ice. Meaning that the Earth wasn't simply frozen, but when the thaw arrived, it released its breath after holding it. Okay, Let's pause for a second. Rocks may appear to be inanimate objects, however, they are also storytellers, patient, stoic, and full of information for those who are able to listen. They have experienced earthquakes, storms, and crawl of continents, and they recall how amazing it is that we may piece together such a far-off chapter. Using hints found in cliffs and outcrops, the rocks tell us more than that there was a Snowball Earth, but how did the oceans react, and how far did the ice spread, and how life endured the cold. And we also discover the seeds of what followed was a resurgence of warmth, and perhaps even the start of the magnificent, intricate life experiment. But we're not quite there yet. However, we must first comprehend how Earth managed to avoid the freeze, because it didn't simply melt in the spring like a typical snowman. Instead, it required millions of years of silent volcanic effort to erupt one burp at a time. Carbon dioxide was released into the atmosphere before the world got in. Chapter 5 will ride the rising tide of CO2 into one of the most favorable temperatures to break the cycle. Remarkable climate reversals over the history of the Earth, but imagine the peaceful purity of old stone, its resonant memory, and how occasionally they imagine the Earth frozen in ice. The stories that are told in the coldest locations are the warmest, silent and shimmering, like though the whole world had stopped to catch its breath, for oceans have been concealed by frozen caps in the atmosphere for millions of years as glaciers have slid across continents. Quiet and chilly, but something is going on beneath the surface. Even while the Earth may have frozen over, the core beneath it continued to burn. Volcanoes with a thick layer of glacial ice are erupting non-stop. Silent release of carbon dioxide into the atmosphere. The secret to Earth's greatness is to persevere like a kettle on low fire. Let's begin with some background information about escape in typical temperate climates. Rain eventually draws CO2 from the volcano and it absorbs it back into the Earth. Carbonates are created when it combines with silica-containing rocks in the atmosphere and is washed into the sea. Is a beautiful cycle that is a natural part of the Earth thermostat. But when the thermostat malfunctioned during Snowball Earth, the land was the waters were blanketed by ice, weathering the primary process that eliminates with no rain soaking into rocks or rivers carrying carbon into the atmosphere. So too had all but halted the water, so that all of the volcanic gas remained in the atmosphere. Over millions of years, building up like steam in an enclosed toilet, the one burp at a time, the atmospheric CO2 content gradually increased. Here's where it gets interesting. CO2 is a powerful greenhouse gas. Heat is trapped closer to the surface the more of it you have, even if kilometers of ice cover that surface. And finally, the atmosphere reached a scientists believe that CO2 levels may have increased to 350 times greater than they are now at the key tipping point. Temperatures that go beyond simply raising the thermostat. Instead, it exposes the entire system to the sun, which causes it to defrost. It wouldn't have happened right away, like turning on a switch. But at some point at which the ice feedback loop caused by the warming from all it trapped heat started to overwhelm the glaciers that had previously marched, sea ice fractured and melted as it started to retreat toward the equator. The white mirror of water pushed on the Earth's surface began to dim, and suddenly, as soon as the ice started to melt, the reflected ice's albedo effect caused things to intensify. Water absorbed and powered cooling began to operate in reverse. Over the darker land, more heat from the sun, which melted more ice and absorbed more sunshine. A greenhouse effect that is out of control, but in the direction of warming. This geological evidence indicates that temperatures not only rose back to comfortable levels throughout time, but also it's possible that average global temperatures have increased to tropical levels. Perhaps even reaching the ground had changed. From a snowball to a sauna in places with temperatures between 50 and 122 reacted with frantic delight after being capped and motionless for millions of years. Now that the ice was gone, they agitated icy stratified waters that were mingled together. As nutrients that had been trapped in warmer strata rose to the surface, the seas became bowls of carbon, sulfur, iron, and oxygen in a chemical soup. And this is when the cap, the distinctive limestone strata that sit atop glacial debris, were created by carbonates, which we discussed in Chapter 4. As carbon dioxide from the atmosphere dissolved into ocean water, they rapidly formed in the warming oceans, and as calcium carbonate precipitated out, a planetary sigh was captured in stone. But as the glaciers receded and melted, the land was abruptly exposed to water and air once more, and severe deterioration followed. Floods surged across rivers that were cut by torrential rain. Naked rock, a period of geological renewal during which rates of erosion were so great that changed whole landscapes. With volcanoes that were no longer stifled by ice releasing ash and gases into thunderstorms screamed as lightning shattered the tumultuous skies over recently uncovered coasts. If the icy silence of Earth had served as a lullaby, after millions of years of survival, what about life? Thor was a drum solo. Microbial colonies unexpectedly discovered themselves swimming in gloomy refuse. It felt like a journey from a dark dungeon to nutrient-rich, oxygenated waters. Under bright lights, you can consume a smorgasbord. According to some scientists, this time period caused an evolutionary boom, precursor to the Cambrian explosion, which would ultimately bring about sophisticated multicellular life. In the upcoming chapter, elaborate further on that. But for now, simply sit with the sheer drama of it all. A world covered in kilometers of glacier ice that was once frozen solid had overturned, swung abruptly into a deluge of heat and chaos, the kind of change that makes you thankful for the generally dull weather we had today. If naturally, this does not imply that everything went smoothly. The post-thaw Earth was a chemically unstable environment, and since biological oxygen levels didn't increase suddenly, many life forms most likely didn't make it through the transition. But for those who did, the stage was set. It serves as a potent reminder to make a significant and unpleasant change. As you fall asleep this evening, remember that drastic change can pave the path for progress. Imagine the Earth's glaciers gradually receding like shadows before the waters rise, microbes and dawning sunshine dancing on waves that haven't been seen in millions of years, blinking in the light, as they get ready for their upcoming big performance in Chapter 6. Following thaw, the Earth is altered. The glaciers have vanished, but their impact remains on the planet. Has just started. The air is dense and the glaciers have receded. Oceans churn and humid rivers roar, slicing across recently exposed rock. Froth and sunlight reaches the equator. For the first time in millions of years, welcome to Earth rebooted without having to go through a sheet of ice. The Great Melt was a global upheaval rather than only a temperature change, a change from motionless to turbulent, from frozen to active. Imagine changing the environment from Antarctica to supercharged for rebirth. Within a few thousand years, the greenhouse was chaotic, violent, and altered everything, starting with the terrain, which didn't change after the glaciers melted. Easily vanish into the Earth without a trace, releasing enormous amounts of melt. As water rushed into the seas from the continents, sedimentary torrents were pulled by the current, carrying silt, sand, gravel, and newly exposed rock surfaces. The entire mountain slopes were subjected to unprecedented erosion. Rapidly bare river systems created valleys and sculpted shorelines. The altered Earth appeared as though a highly passionate cosmic force had pressure washed it. Geologically speaking, the newly exposed crust was experiencing hyperactivity at this time. Acidic rain and CO2-rich air caused a strong reaction. After these reactions eliminated CO2 from the atmosphere, the Earth's thermostat returned to equilibrium. And then remember how the oceans were mostly locked off during the snowball period, areas that are layered anoxic and separated from the atmosphere. However, oxygen mixing and a plenty of nutrients accompanied the thaw. Scientists refer to phenomenon as ocean fertilization, since it caused all the iron and phosphates that had gathered in the depths now rushed to the surface, fueling a microbial life explosion. Bacteria multiplied, algae blossomed, and photosynthesis entered overdrive. It was the planet's first significant biological boom in many respects. Imagine living in a world where the oceans are green with microscopic life, but this biological party's teeming, swirling respiration had an additional effect. The atmosphere's oxygen content started to gradually increase, for billions of oxygen had been stored in rocks for years and mostly produced by cyanobacteria. Now that oxygen had a place to go, there was a reason to stay in the deep ocean. Scientists observed that the chemistry of the ocean and atmosphere is maintained in the rock record as stable. Isotope changes suggesting an increase in oxidized sediments involved in carbon cycling, demonstrating a greater supply of free oxygen. And those well-known cap carbonates which we previously discussed formed rapidly in the remaining warm, mineral-rich waters. The post-glacial world was in disarray following the thaw, yet fertile, and something remarkable might have started amid that chaos, laying the foundation for complex life prior to the snowball events. Life was comparatively single-celled organisms, and basic microbial mats are a very slow party, evolution-wise, but the snowball Earth's environmental stress, which was followed by the oxygen-boosted nutrient-rich repercussions, might have accelerated evolution. It's similar to trimming a tree. There is even a belief that when the sun returned, growth blossomed from every node, despite the freeze severely cutting everything back. That the Cambrian explosion, which would take place tens of millions of years later, was facilitated by this post-phase. Later, multicellular life did not emerge right after the glacial period melted, but the planet's circumstances improved more than ever before. Was wetter, warmer, and nutrients were rising due to chemically enriched oxygen, where many ecological niches started to emerge. Consider it the planet's handing we're giving away golden tickets to the upcoming evolutionary experimentation phase. And now, all of this humility, every glacier, every stone, every evolutionary spark acted out on a planet where there are only germs, no humans, trees, fish, or birds, period, and a constantly changing globe. It's encouraging to know that our every breath we take has a connection to a long-forgotten past, because the contemporary world is based on such a rich past. After an ancient thaw, algae grew, so when the Earth warmed, it didn't simply repair it. The forests weren't yet here, and were primitive creatures found in shallow coastal waters such as dinosaurs or even jellyfish. soft-bodied blobs and colonial plankton were the first multicellular organisms to emerge. The earliest sponges were basic ones, hardly distinguishable but definitely the first after the snowball. The planet began to become more complex as deadly volcanoes continued to rumble. CO2 levels stayed high for a while storms raged, but the frost had ended and motion color and the emergence of the modern Earth as we know it came with it. Let's also take a moment to recognize the lessons we've learned from this period of Earth's history. Earth's tail snowball has evolved into a model for comprehending planetary feedback. See how minor adjustments can have a big impact on the world's climate resiliency even in the most severe circumstances. Life can endure, and even exoplanetary science can demonstrate how frozen life may exist behind the frozen shells of worlds orbiting other stars in an odd manner. Snowball Earth teaches us that the climate is not stable, which makes us realize how fragile our current situation is. Fix that stability is a valuable but transient state and that life is not guaranteed. Gift. So while you fall asleep tonight, picture a world that has just thawed and rivers cascading, breathing deeply for the first time in a long time while traversing pristine landscapes and coastlines, microbes dividing and swimming in the warmth for eons, dreaming of what they may turn into, and we'll examine that in our upcoming chapter. Chapter 7. The lights for complex life start to turn on as the Cambrian curtain lifts. The planet has warmed, the glaciers have melted, and for the first time in ages, in addition to healing, Earth is becoming more ambitious. Welcome to the Precambrian period could be compared to the subdued prelude to a magnificent symphony. Silence and cold have given way to a bustling, swirling ecosystem of microscopic life on Earth. But something new has emerged, is causing the shallows to become more complicated. This is the time frame before there will be a biological invention boom similar to the Cambrian explosion. Although that revolution began some 541 million years ago, its origins were planted in the moist, warming aftermath of Snowball Earth. Let's take a moment to look back at what life was like on Earth for billions of years following the thaw, which are simple, single-celled creatures such as bacteria and archaea. But following Snowball Earth, the groundwork is being prepared for the ascent of eukaryotes, cells possessing organelles, nuclei, and the ability to work together, and multicellular follows collaboration. It began modestly as clumps of cells clinging together, sharing work, and experimenting are all examples of many things. Some cells used specialization to handle nutrition, while others assisted with construction. Although these early team endeavors may not sound spectacular, they served as the initial prototypes for what would eventually become plants, animals, fungus, and eventually one of the stars of this new era was a group, which included ourselves and the early players, called the Ediacaran biota after Australia's Adia Hills. These soft-bodied, extraterrestrial-looking creatures were found in the area where they initially appeared. They were flat, frond-like, or blob-shaped 575 to 541 million years ago, and they preserved the earliest big remains of sophisticated life without bones, claws, or jaws. The Ediacaran creatures were merely impressions in the silt, resembling the spectral shapes of long-forgotten dreams. Strange, amazing, and incredibly enigmatic. Some appeared to be leaves, while others there were defiant shapes, discs, and tubes in the quilted cushions. Classification. Were they huge amoebos, fungus, or animals? They allude to the experimentation, but it's still unclear if it's something else entirely. Occurring in this newly fruitful planet following the increase in freeze oxygen levels, the expansion of shallow marine habitats, and the stabilization of nutrient cycles were ideal circumstances for evolution to attempt something daring. And then the approximately 541 million years ago, during the Cambrian period, life we refer to this explosion of diversity as the Cambrian explosion. But imagine a conflagration like this was more akin to a celestial dawn. As light first revealed the hidden hues of life in Cambrian seas, animals with suddenly organisms with hard shells, joined legs, eyes, mouths, and motion arose, resembling armored, segmented, and furiously armed trilobites. Successful Anomalocaris is a strange predator with a revolving mouth that resembles a shrimp. The reasons behind Waxioopabenia, these weren't merely different bodies. The hallucinations. Names were as bizarre as the animals themselves. Among these were new opportunities for swimming, burrowing, and predation. Sensing that evolution had settled into a rhythm, it began remixing in all directions. To be clear, the Cambrian boom was not caused by Snowball Earth, but it probably started by trimming the snowball to create the stage. It's possible that glaciations served as an evolutionary bottleneck, eliminating weaker lineages and enabling survivors to too quickly diversify later on. By nourishing the post-glacial world was abundant in oxygen, nutrients, and natural space. And third, by opportunity arises from disruptive change, and Earth had recently seen a drastic metamorphosis, as if the planet had moved the rules around the chessboard and then gave biology a completely different set of components, and the biosphere on Earth was never the same. Once more, life started to become more sophisticated, layer by layer, predator by layer, and the skeletons, neurological systems, and ecosystems of prey with each million years that went by. The web of life became more complex and varied, evolving from a frozen planet to a bursting, blooming one was a biological phenomenon as much as a geological one. Pivotal moment when the snowball's end started the lengthy evolutionary arc that would eventually lead to philosophers, fish, flowers, forests, and this comforting idea before going to bed. Every single cell, gene, and component of you, since you are more than just stardust. Every breath may be traced back to something that survived that freeze. You are composed of resilient molecules that were once able to float in ice, seas, and persevered. So imagine those first sophisticated organisms floating gently while you sleep tonight, not in a hurry, but in warm Cambrian seas. Just the lights were turning on as the current, learning to move, to perceive, to evolve. The curtain had raised, and life was prepared for the upcoming major play. The discussion then shifts to a scientific dispute in Chapter 8, where we'll gently explore the realm of academic disputes, slushball hypotheses, and the reasons behind them. Scientists enjoy debating the science of rocks, despite the fact that teaching occasionally isn't about stating unchanging truths and going on. It resembles a continuous, courteous, and occasionally impolite argument. It spans several decades, or even centuries, especially in the case of Snowball Earth. The Snowball Earth theory is still up for discussion. Its elegance and drama have not gone unnoticed. In fact, they have provoked one of the most intriguing and sometimes heated discussions in contemporary climate and geology, because although it sounds lyrical to imagine a world completely covered in ice, not everyone believes it was actually that way. So, let's begin with a really difficult question. Was the Earth actually a survivor of that extreme cold? We are the heritage of that perseverance, the warmth that followed the ice. So as you sleep tonight, find solace in this odd and lovely idea that the Earth has burned, flooded, and frozen solid, witnessed almost everything come to an end. But here we are. Snowball Earth didn't ruin life. It humbled it, it improved it, and ultimately it influenced the intricacies seen in oak trees, coral reefs, and your own hands. Today we will depart from the ancient past as we go into the final chapter and return to inquiring as to what lessons this icy chapter can impart to the present world. So close your eyes and visualize a peaceful, frozen planet that is now rotating silently through the night, bearing the promise of ice and the remembrance of life. So we have completely circled back from a frozen, glittering world to one that is seething with tremendous depth and warmth. From a quiet, interrupted only by the glacier's gradual grind to the Earth was more than a snowball, a symphony of life in all its infinite variations. It was a test chapter in geological history that almost completely obliterated life, but perhaps possibly molded it into something more inventive and resilient, and even more amazing. Tonight we traveled through hundreds of millions of years, past the Proterozoic's primordial glaciers and into freezing seas and volcanic pulses, into the early stages of complex life, and across the great Thor life peaked in discussions among geologists based on evidence trails, buried in stone, and even conjured up far-off ice worlds that could be similar to our own dark history. But ultimately, Snowball Earth may have taught us the most important lesson, provides us with a perspective of our planet's vivid blue color. This place we call home has experienced chaos, extremes, and life over and again, has come out of the cold alive, unharmed, and unaltered, and perhaps that's something to keep with mind, particularly at this moment when our climate is changing again. As evidenced by the Snowball Earth, we are aware of the vulnerability of the systems we rely on, as well as the potential for resilience when circumstances change. Each cell is a product of survival. Therefore, as you go to sleep or allow your as my mind wanders, I'll end by asking you the same silent questions I posed at the start. Where in the world are you? What time is it where you are? And have you been listening to this narrative since tonight? Calming or a bit too fascinating? If you're still conscious, I hope you discovered the journey valuable and perhaps gained new knowledge in the process. And I hope your dreams, if you're already asleep, are filled with floating countenance, bubbling underwater vents. And before you leave or drift out entirely, you can see snowflakes falling on ancient oceans. I would really appreciate it if you liked this video and subscribed for more drowsy science videos. One bedtime story at a time, it fosters the growth of the drowsy scientist and helps him discover the mysteries of the cosmos. I appreciate you spending this time with me despite the fire and the frost, and good night. I hope your world remains warm and full of fascinating things. Snowball, or merely enter the alternative theory of slushball Earth, a little slushy. Although glaciers did reach near the equator, according to the slushball Earth model, the equatorial oceans in this version of Earth, they might have stayed at least mostly ice. I saw a harsh cold age, but maybe not a total shutdown. With slushy oceans encircling, it's a touch less dramatic with sea ice instead of a planet encased in glass. But additionally, one of the primary arguments might be a bit more tenable, that an issue that would arise if the entire world were to go into full snowball mode is how might photosynthetic organisms have survived being frozen over with a kilogram of solid ice? How could any light get to the water behind that freezing cover and survive? Snowball Earth proponents cite geothermal hotspots in thin equatorial ice, perhaps a remote haven where people managed to survive, although detractors claim that a completely frozen the slush ball model provides life where the ocean would have made it nearly difficult for surface-dwelling bacteria to survive. A few more crevices to conceal oneself in. And then there's the problem of ice thickness. In order for Earth to fully snowball, ice sheets up to a kilometer thick near the equator would probably be needed. That's a lot of ice, which begs the question of whether such dense layers could have developed at all without totally stopping. The rain, snow, evaporation, the hydrological cycle, everything on Earth, the climate must continue to change. And how did enough if the oceans were closed off? Wouldn't the ice itself have slowed volcanic outgassing or decreased the amount of CO2 that would have built up to escape the freeze? Impact of greenhouse warming. These are legitimate inquiries, in fact, and some studies also note that they keep scientists up at night, but hopefully not our drowsy viewers. The geological record contains errors and discrepancies. For instance, in some areas, normal weathering of sedimentary strata generated during the glacial period indicates the presence of other deposits, and flowing water appear to indicate glacial cycles rather than a single. These hints may indicate a more dynamic climate than a persistent frost. Although a complete static freeze might be possible, proponents of the snowball concept have responses. They think that refugia under thin air or close to hydrothermal vents, even in the event of a worldwide freeze, life might still exist on ice due to volcanic CO2. It's possible that accumulation over millions of years that isn't removed by weathering could intensify the greenhouse effect, sufficient to cause a disastrous melt, and many of the alleged discrepancies in the rock record can be accounted for by geographical differences, geological peculiarities, or even post-glacial. Additionally, the snowball model does a neat job of revising the argument of simplicity and coherence, work of explaining the abrupt re-emergence of cap carbonates, the worldwide distribution of glacial deposits, and the remarkable chemical changes in rocks worldwide. Yet ultimately, this is about the nature of science rather than a tale of one side being correct and the other being incorrect itself, as science depends on ambiguity, close examination, probing, and yes, but what if, and prodding. And Snowball Earth is an ideal playground for that interest, situated at the nexus of biology, geology, climatology, and even with hints dating back billions of years. Planetary science is a puzzle with no simple solution, provides the kind of mystery that motivates scientists to travel into the frigid landscape or pack their bags for lonely Namibian outcrops, hills of Canada, merely to chip away at a few old stones. The argument goes on without yelling, but with late-night disputes over sediment cores and isotope ratios even now. With the development of fresh evidence and computer models, coffee and core samples, as scientists get more advanced, they continue to struggle with the specifics of how many did snowball occurrences occur, how thorough was the freeze, what preceded it, and some even inquire as to whether Snowball Earth might occur once more. But don't worry, it won't. We're regrettably moving in the opposite direction, probably anytime soon. And although the exact appearance of the planet 700 million years ago may never be known, the argument itself is incredibly valuable, sharpens our instruments, broadens our creativity, and compels us to reflect carefully on the criteria for making a planet habitable and the fine distinction between one that is teeming with life and one that is frozen over. As you curl up under your blanket tonight, consider Earth as more than just a location, like a puzzle or enigma covered in rock that is gradually solved by a patient, fervent those who respectfully debate hints that date back billions of years. As well as in Chapter 9, we'll examine why Snowball Earth is still important, only to lab-wearing experts, but to everyone on our delicate, dynamic planet at first glimpse. Snowball Earth may appear to be an archaic curiosity from those prehistoric times, peculiarities from a place so far away that it's practically legendary, and frozen chapter, hidden in billion-year-old rocks that geologists are studying with dusty field notes and wide-brimmed hats. However, if you look more closely, you'll notice something unexpected. Earth matters today. Now more than ever, let's begin with the broad overview of the Snowball Earth. More than anything else, hypothesis provides us with a window into the Earth's climate system, not only how it acts in typical circumstances, but also how it acts with severe stress, because this was a full-scale world disaster rather than merely a cold snap. Reconstruction of a frozen ocean, a halted hydrological cycle, and life clinging to bacterial fingernails. Followed by a thaw reverse. It's a tale of feedback loops that may have finished with tropical temperatures at the poles. Because it was so severe, climate tipping points of fragile balances that, given the correct push and encouragement, can go completely out of control. That has some very contemporary and genuine ramifications, as we are currently dealing with our own climate issues caused by human activity rather than by tectonics or waning sun's axe. Ice is melting, greenhouse gas levels are rising, and systems are understanding Snowball Earth in a different way allows us to question what happens when feedbacks speed up, how the planet reacts to drastic changes in the atmosphere, what are the long-term effects of upsetting the balance of the global climate. Snowball Earth is similar to Earth's stress test, showing how adaptable and how delicate this system is. But there are more snowballs on Earth. So it's not just, it is pertinent to climate scientists and has emerged as a key concept in the hunt for extraterrestrial life: planets. Let's take a moment to consider the colder regions of our solar system, where there are icy moons despite having frozen exteriors. Europa and Enceladus have subterranean oceans that might conceal heated vents and odd sounds from gloomy environments. Similar to how life on Earth might have endured the snowball epoch by hiding beneath ice oases or clinging to geothermal vents. In fact, extraterrestrial life may flourish in such obscure niches when astrobiologists frequently use Earth's extremes to simulate what life might look like elsewhere. Direction Snowball Earth becomes into a sort of biological reference guide. Investigate whether life could persist when Earth resembled a frozen cue ball. Perhaps it could do the same on another planet while spinning through space, doing it at the moment. Which leads us to a somewhat more philosophical point. Snowball Earth reminds us that complexity is brittle and that life is resilient but not unbeatable. Hard-won success, that breathable air and thermal stability aren't our worlds. Everlasting features are gifts that are fleeting, priceless, and profoundly linked. It's simple to overlook how drastically our planet has altered over time. Its history is filled with extreme changes, major extinctions, and teetering on the brink of both fire and ice. Unlikely recoveries, but keeping these things in mind helps focus on the here and now. Therefore, studying Snowball Earth teaches us about how planets function rather than merely allowing us to glimpse into a bygone era. Ecosystems persist, how life changes or vanishes under stress, and perhaps we're also discovering a little bit about ourselves in a subtle way, because every human, plant, animal, and fungus on Earth is descended from a